First thing we need to look at is the exposure class. So when we're looking at the exposure class, we're going to be taking a look at page 190 and tables 11-2 and 11-3. What we do is we take a look at the actual use of what the concrete is going to be used for. So in this case here, it is a concrete slab, an underground concrete slab. So it's not going to be exposed to freezing and thawing, but it will be exposed to chemicals. So we see that our exposure class is C4. When we also take a look at the exposure class properties in the next table, we see that there's a couple of other things that we want to take a look at. So our F prime C is going to be 25 MPa. So this is the strength of the actual concrete that it needs to be at 28-day strength. And we have a maximum water cement ratio of 0.55. Okay. Next, we're going to take a look at the design strength. So when we're looking at the design strength, what we're doing is we're going to determine a value that's going to be more than F prime C. So we need to have a design strength that's more than 25 MPa because that's our required strength. Our design strength needs to ensure that when we do end up making this concrete, when we actually test it 100 times out of 100, we have to actually meet our 25 MPa. Okay, so the design strength reference is on page 228, and we see two different formulas. Okay, so let's take a look at a couple of things. So F prime C is our required strength in MPa, and that is 25 MPa. And we're going to go F prime C R is going to be our design strength. Okay, so equation (12-1), we're going to have an F prime C required, or design strength, is equal to F prime C plus 1.4 times our standard deviation. As indicated, our standard deviation for this particular design mix is 2.0. So we're going to go ahead and plug that in. And we're going to find our F prime C required is equal to 25 MPa plus 1.4 multiplied by 2.0 MPa, okay, which equals 27.8 MPa. Okay. When we take a look at the second equation, we're going to look at F prime C design is equal to F prime C plus 2.4 times our standard deviation minus 3.5 MPa. Okay. So when we're doing this, this looks like 25 MPa plus 2.4 times 2.0 minus 3.5. MPa, which brings me to 26.3 MPa. Now, when we take a look at both of these equations, what we do is we determine the highest strength that's going to be used. So in this case, we're going to make a concluding statement saying that our design strength is equal to 27.8 MPa. Okay, then we have our water to cement ratio. Okay. Water to cement ratio is going to be found on table 12-3 on page 221 and figure 12-2. So when taking a look at the figure, we take a look at our little bit of a graph that we have here. So we have a graph, right? And we have our F'3, which are F'(C), which is our strength. And then we have the actual water to cement ratio down here. All right, so when we look at the two values here, so if we're looking at it between 0.54 and 0.61, right? And we're going up to 25 and to 30. Okay, we see two values, right? So if we look at the chart to find the actual values of these, we're going to have a point at the 30 strength at the 0.54 water to cement ratio, and at 25 MPa strength, it's going to be a 0.61 ratio. Okay, so this line, when we look at it, is a straight line. So what we want to do is we want to be able to take and find the difference between 5.4 and 0.61, because we know that our F'(C) required is 27.8 MPa. So we can do one of two things. We can find the 27.8. So let's go ahead and just erase a couple of things here. So 25, so this is 5 here. Oh, let's redo our line. Okay, so with 25, 26, 27, 28, so this are 27.8 would be right here, right? And if we were to kind of draw that line straight across to where we hit that line, we would actually see that it comes right down, okay? 25, 5.4, 5.6, 5.7, 5.8, 5.9, 6, 6.1. So this is 5.5, 5.6, 5.7. So 0.57. Okay, and when we look at that, we have to remember though that our exposure class, right up and over here, right up in the actual water to cement ratio, indicates that our maximum water to cement ratio can only be 0.55. So our water to cement ratio here, just by looking at the graph, our water to cement ratio is going to be 0.55. If you wanted to figure that out mathematically, what you would do is you would find 2 points in between the lines. So essentially, let's go ahead and label these guys. This will be A and B, okay? And what we would do is we would find our water to cement ratio at A. So essentially what we would do is we would find the slope of the line, and we would go, this is going to be the actual water to cement ratio would equal 0.54, which is the number that we're starting with, and we're going to add the difference between the two lines. So we would need to find the water to cement ratio of A subtracted by the water to cement ratio of B, okay, all over our F prime C at A minus our F prime C at B. Okay, so this gives us the slope of that line, right? And then let's go ahead, and that would be all multiplied by F prime C required, right, minus F prime C of B. Okay, so that looks like okay, so that would equal 0.54 plus 0.61 minus 0.54 all over all over 25 minus 30 multiplied by 27.8 minus 30. Okay. When we look at this, and when we go through the math of this, it gets to 0.571, which is actually pretty close to what we had seen in our chart, right? But again, because our maximum water to cement ratio is indicated at 0.55, and that's what we go with. All right, we'll get on to our next page. Okay, our next item that we're going to take a look at is air content. Air content can be found on table 12-5 on page 223. Okay. By taking a look at this table, you're going to take a look and see that there's two rows that identify for non-air entrained concrete and air entrained concrete. And each of the columns will identify the nominal size of the coarse aggregate. By taking a look at our requirements page, we've identified that our aggregate size is 20 millimeters, and we are making non-air entrained concrete. So when we take a look at this, we see that the air content is going to be air content is equal to 2%. Okay. Then we take a look at our slump. Right. So when we take a look at the actual paragraph on page 225, we notice that any concrete with a maximum slump identified of 80 millimeters or more has a tolerance of plus or minus 20 millimeters. So taking a look at the table 12-6 on page 224, we see that the type of concrete that we're making has an indication that it's going to be, our specified slump is going to be between 25 and 75 millimeters. So our specified slump is between 25 millimeters and 75 millimeters, plus or minus 20 millimeters. So this means that when we actually measure our slump next week, when we mix our concrete, we'll see that we should have a slump of anywhere between 5 millimeters and 95 millimeters, which would be acceptable. Now that we all know all of this, we can look at our water content. Again, taking a look at table 12-5. On page 223, we can now plug in the next value that we need to know, which is the slump. So when we're taking a look at non-air entrained concrete with a nominal size of 20 millimeters and the slump being at between 75 millimeters, or the slump being 75 millimeters, we see that the water content is going to be 205 kilograms. Now, we're going to need to adjust that at the end for the absorption rate of water, because that aggregate is actually quite dry, and we need to make sure that we make that assumption. Now that we know our water content, we can find our cement content. Okay, and we don't need any tables for this because we know our water to cement ratio is 0.55. So water over cement is equal to 0.55. We know what our water content is, so we're going to go 205 kilograms over cement equals 0.55, right? And when we do this, cement then all right, the next thing that we need to take a look at is cement is then equal to water over 0.55. We know that our water is 205 kilograms. And our water to cement ratio is 0.55. So our amount of cement that we need is 373 kilograms. Okay. Next, we're going to take a look at our coarse aggregate requirements. So coarse aggregate content is found on page 12-4 on page 222. Okay, so what we want to do is we want to first determine a factor of what we're going to multiply the relative density of coarse aggregate in the 1 meter cubed volume. There's a multiplication factor that we need to multiply that by to identify how many kilograms there are. So when we look at the actual table, we see that the finest modulus listed is 2.4, 2.6, 2.8, 3.0. If we were to increase that by 3 to 3.2, or the next value, we then would identify what the factor would be, being 0.66, 0.64, 0.62, 0.60, and if we were to take a look at that at 3.2, it would be actually at 0.58. So our factor that we multiply our coarse aggregate density by is 0.58. Now that we have that factor, what we do is we're going to take that factor and multiply it by our density of coarse aggregate. Okay, so in this case, our factor is 0.58 multiplied by 1,600 kilograms per meter cubed, right? And when we do this, we see that this is going to be 928 kilograms per meter cubed. And we know that we're actually making 1 meter cubed, so 928 kilograms is what we need. The next thing we need to consider is admixtures. Admixtures, as you know, will either change the color or the properties of the material, typically superplasticizer or air entraining agent to add air into the concrete. In this case here, we are not making any air entrained concrete, and we're not making any concrete with admixtures. So we do need to label that we have an admixtures, but we ensure that we just make sure that we let people know that it's not applicable. We're not applying any. All right, here's the fun stuff. Fine aggregate. So let me just draw a little picture here before we move forward. We're creating a mixed design to be able to make 1 cubic meter of concrete. So it's 1 meter by 1 meter by 1 meter, right? And we've already established that we have and need 928 kilograms of coarse aggregate. We've already identified that we need 205 kilograms of water. We've already identified that we need 373 kilograms of cement. And we know that there is 2% air, right? And 2% air is essentially a nice way to be able to identify how much air is in here. So when we're taking a look, our air content with 2% air is 0.02 meters cubed, right? Now, what we're going to do now is we're going to transform all of these values into volume so that we're going to find the missing volume, which is our fine aggregate for our concrete. So let's go through that process now. Okay, so because we know the mass of our water, our cement, our coarse aggregate, we're creating that absolute volume of 1 cubic meter, we're going to start with a little bit of a formula here. So volume is equal to mass of material all over the relative density of that material to water times the density of water. Okay, so what we're going to do here is we're going to find the volume for water. In this case here, our mass of that material is 205 kilograms. All over the relative density of water to water is 1. Multiplied by the density of water, which is 1,000 kilograms per meter cubed, right? And when we do our math here, our volume of water is 0.205 meters cubed. Right, and we're going to continue that with our cement. So cement is 373 kilograms all over 3.15, which is its relative density to water, and that's given in our details on our lab sheet. And we see that it's 1,000 kilograms per meter cubed. And when we look at this, it's 0.118 meters cubed. Okay, I'm just rounding to 3 decimal places here. Our coarse aggregate is equal to 928 kilograms over its relative density, which is 2.68 times 1,000 kilograms per meter cubed, which equals 0.346 meters cubed. And finally our air, which as we identified is 0.02 meters cubed. Right? So when we add all of this up, or 0.02 meters cubed, when we add all of this up, what we get is 0.689 meters cubed, right? And what we then know is if we were to take that 1.0 meter cube and subtract our 0.689 meters cubed, right? We have a fine aggregate volume, which is equal to 0.311 meter cubed, right? So that's really nice because we can take this formula that we identified up here, right, and bring it back down, right? And what we're going to do here is we're going to change this a little bit. We're going to take a look at our formula for finding the mass. So in this case here, the mass is equal to the volume times the density, times the relative density times the density of water. Okay, so if we plug these values in, we see that our fine aggregate is going to equal the volume, which is 0.311 meters cubed, multiplied by its relative density to water, which is 2.64, multiplied by 1,000 kilograms per meter cubed, right? Our meter cubes canceled out. And when we see all of this, we find that we need 821 kilograms of water. Okay. All right, so we have our mass that we are required now. So we have our water, which is 205 kilograms, which is our design volume, design mass. We will need to adjust that. We have our cement, which is 373 kilograms. We have our coarse aggregate, which is 928 kilograms. And we have our fine aggregate, which is 821 kilograms. Okay. We do need to calculate for moisture absorption or moisture correction. Right? So whatever percentage is, the example that I'm going to give here is so with our water, cement, coarse aggregate, and fine aggregate, we need to find our moisture correction, which is 1.2% and 1.8%. So our coarse aggregate, we multiply the percentage by the mass to get how much we need to modify our water content by. So in this case, we have 11.1 for coarse aggregate absorption, and 14.8 kilograms for fine aggregate consumption. So what we need to do then, therefore our actual water value is going to be 205 kilograms plus 11.1 plus 14.8. And our total in this case here is going to be 230.9, and we round it to 3 significant figures, 231 kilograms. So when we're looking at our values now for calculating, our values now for calculating how much we're going to need for 0.03 cubic meters, right? Because all of these values that we've just found out are for 1 cubic meter, right? So actually, let's just put it up here. I'm going to do this over here. Right? So let's bring this over here. So this is for 1 cubic meter. This is for 0.03 cubic meters. Right? So our value here, our actual water content, is actually going to be 231 kilograms. Right? And if we multiply that by 0.03, which is 6.93 kilograms, and so on and so forth. So we would multiply this by 0.03 to get our value over here. And I'm going to leave that for you guys. I've just gone through the entire lab except for identifying how much mass we need for each of our materials next week. But that is essentially what we're going to do. If you have any questions, don't hesitate to reach out in an email. But that is essentially how we go through our lab this week.